Okay. Hi, I want to talk about our new result on Steiner forest, which is a better than two approximation. We designed the first better than two approximation algorithm for this problem, which is a joint work with Ali Ahmadi, Iman Gholami, Mohammad Hajiaghayi, and Mohammad Mahdavi. So let me start with defining the problem. Now, in a Steiner forest problem, we are given a weighted graph and a set of pair of vertices. And the goal is to select a subset of edges such that vertices in each pair are connected through these edges. And we want to minimize the total cost of the edges that we are selecting. This problem is a generalization of the Escherichian tree problem. So in Escherichian tree, again, we have a weighted graph. This time we have a set of vertices that we call them terminals. And we want to select a subset of the edges of the given graph such that these edges span all the terminals, connect all the terminals together. And again, we want to minimize the total cost of the edges that we are selecting. And this problem is a generalization of the minimum spanning tree problem. So for the HNA tree, there is a trivial two approximation algorithm, but there are a lot of improvement on this. So it starts with 11 over 6 approximation factor of Zherkovsky. And right now, the best approximation factor is 1.39 by Birka, Grandoni, Roscos, and Sanita. But for HNA forest, since the two approximation algorithm of the Agrawal-Klein Ravi, which also Gomez Williamson generalized and refined that their algorithm. So since then, there is no improvement on this on the approximation factor of this problem. There were some works that try to analyze some natural algorithm for this problem, like 96 approximation factor that use a greedy approach and 69 approximation algorithm that use a local search approach. And we were able to design the first algorithm that has a better than two approximation factor for Shan forest. So our algorithm has a 2 minus 10 to the minus 11 approximation guarantee. And along the way, we also designed a 1.94 approximation factor for Shan theory, which is not a best approximation factor for Shan theory, but like it was crucial for us to design our Shan forest algorithm. And let's see the overview of our algorithm. So we start with the legacy mode scoring algorithm, which is a name we gave to the two approximation algorithm. And then we run a local search, and the solution we get here is like a it has a like 1.94 approximation value for Shine theory. But for Shine first, it's not in the local search is not enough, so we have two different passes to get two different new solution. One of them uses AutoCAD pair, the other one is extension. I'm going through the detail of all of this. But at the end, we show that the best solution we get among all of this is like a better than two approximate solution. Now let me start with the explaining the legacy mode scoring algorithm or the two approximation algorithm. From now on, we assume that each edge of the graph has a length equal to the cost of the edge. And we are going to maintain a forest such that initially this forest is empty, and at the end, it's gonna have our solution. And we are going to define a term active set on the connected component of this forest. So active set are connected components of this forest that need to connect to other components. For example, here, let's assume that our forest is only does it only has this edge. So we have like three components in our forest. So this component is inactive because all vertices inside it are already satisfied. They are connected to their pair. But these two components are active because they need to connect to each other. So through our algorithm, active sets grow and they color its and they adjacent edges like this picture here. And this process continue until one edge become fully colored. After this is become fully colored, we add it to our solution, to our forest. And because we add it to our forest, we need to merge its component of its endpoint. And now we have this new component, and if it's active, it will grow. And this process continue until there are no active sets. It means that all vertices are satisfied, or every component doesn't need to connect to other component. So that's the process, and that's when the process ends. And I want to just mention that, as you can see, the shape of this active set becomes similar to modes. So that's why we call it mode growing algorithm. And when the mode growing process ends, we have this pruning phase, which we just remove any edge that is redundant, it's not necessary. For example, this edge here is not necessary to satisfy, it has fully colored, so we added to our forest, but we don't need it to satisfy any demand, any connectivity demand, so we just remove it. And this algorithm has a two approximation factor. To prove this, we first define a term that we call it total gross, basically total gross of all active set. So for each active set, the duration that is growth, we call it gross duration, and we define, for example, R as the total gross of all active sets. And then we can prove that the optimal solution is at least R, at least the total gross. And the solution we get is at cost at most two times R. And through this, we can prove that we have a two approximate solution. So I'm not going to go through the detail of these two bounds. I just want to say that if in our paper, in our work, we try to focus on improving these bonds. So we try to either find a way to find a better lower bound for the optimal solution, like by some constant factor better, or try to find a new solution that has a better upper bound, was again by some constant factor. So if we can do any of this, we have a better than 12% solution. So the first one is give us some structural property about the optimal solution. I'm not going to talk about this one a lot in my presentation, but I'm going to focus on the second one. So basically, I want to try to show that we can uh, modify the mode scoring algorithm to reduce the total gross of these modes. And after that, if we can say that, okay, the total gross has been reduced by some small fact, by some constant factor, such that it's like significantly smaller than the cost of the optimal solution, then since our solution, the solution we get through this new mode scoring algorithm, costs at most two times the total gross, we have like a better than two approximate solution. So now we want to focus on the reducing the total gross of the modes, our modes. So we design a local search algorithm. So first, let me define a boost action. Basically, boost action is like we select a vertex and a specific time, and we force that vertex to remain active until that specific time. I mean, any component that contains this vertex should be active until that specific time, even that component if it doesn't need to be active. And we define two variables for each boost action. There is a win, which say that if we apply this boost action, how much the total gross will be reduced. So win is the reduction in the total gross. And we have this term, we have this variable loss. We say that this boost action, how additional new growth it will introduce, because we are growing some component that they were inactive before this boost action. So we define this win and loss, and then we say that a boost action is valuable if its win is significantly larger than its loss. And then until there is a valuable boost action, we apply it. Each time we apply boost action, we need to run this mode scoring algorithm again from the scratch to like this time we force this new vertex to be active more. So we apply this valuable boost action, and again, if there's a new valuable boost action, we apply it, and so on. We continue this until there is no valuable boost action. And let me show it on an example here. So here we have this Steiner tree instances. We have four terminals and one vertex that is not terminal. And we need to connect these terminals together, and you can see the optimal solution, connect them to this center vertex. But here, if we run the legacy mode scoring algorithm, because this center vertex doesn't need to connect to any other vertices, its component won't grow. It's not an active set. And we will select edges in the outer of this instance, the edges around this. And we can see that our solution costs almost two times the optimal solution. But if we apply boost action here, you can see that the total growth of our modes has been reduced. So it's a valuable boost action. And this time we will select similar edges than the optimal solution. So this is one step of our local search. Our local search has multiple valuable boost action that we are applying. And then we, and then we define a club property. So to analyze the solution we get from the local search. So club property says that we can somehow bound the total gross. I mean, for any three vertices, we can somehow bound the total gross of active set corresponding to these vertices by the cost of the cloud that's connecting them, any cloud that's connecting them. And here we are mostly interested in a code that is sub tree of the optimal solution. I mean, the way that optimal solution is connecting them. And then we prove it, we have this generalized curl property that we generalize this property for any number of vertices, not just three vertices. And using this generalized curl property, we showed that the local search achieved 1.94 approximation factor for the Shine tree. But it's not enough for a Shine forest because, see, in a Shine tree, we only need to know which vertices are part of the optimal solution. If we know them, we can boost them and we get exactly the optimal solution. But in a Shine forest, the question is not only which vertices are part of the optimal solution. The question is which vertices are in the same component. So it's a more complex question. And if our component, the component we get, is similar to the optimal solution, we can say that each component separately is like a HTML3 instance. So we can somehow analyze the solution we get, and it should be better than to approximate. But the problem is that our components can be different from the optimal solution. So intuitively, I just want to say that there are two different cases. One case is that we have underconnectivity. Basically, uh, uh, we are connecting less vertices compared to the optimal solution. So for example, optimal solution is one component, but we have many components. This is one case, just it's intuitively, but we designed an extension approach that solves on this issue. The other issue can be over connectivity. I mean, we are connecting many components of the optimal solution together and we have like one component for all of them. And we design an auto architecture that solves this issue. So one of these two is like a majority of the issue and majority of the difference between us and the optimal solution. So let me first explain the extension. It's a very simple approach. So we have this mode scoring algorithm, and for each active set has a gross duration. So we now assign a potential to each active set equal to the epsilon times its gross duration, and then we run we run the mode scoring algorithm again. This time, if a mode scoring if a component want to become inactive, but it has some potential or its sub says has a potential, we let it to consume the potential and remain active for a small for that duration of time. So basically, we are just increasing the total growth by some small factor to make sure that we are not under connecting vertices compared to the optimal solution. And why this approach works? Basically, after this extension, either our component becomes similar to the optimal solution. In this way, we can say that, okay, now if we run the local search, we would each component is similar to the initial instances, then we can get a better to approximate solution. But if we still have this underconnectivity issue, I mean, still there are many vertices connected in the optimal solution that after extension we are still not connecting them. It means that those vertices in that, for example, just assume this component of the optimal solution that we have multiple components for it. Those vertices inside that component are too far from each other in the optimal solution that even after the extension we are not connecting them to each other. So that's where we get a better bound, lower bound for the optimal solution, and then we prove that we have a good solution better than to approximate solution. Next, I want to talk about autarky pair, the approach we use to handle the overconnectivity issue. I want to first show an example to see why this can be an issue. Here we have like a n pairs, n horizontal pair, and that connected with an edge with cost 1, and two pairs, the top and bottom pair. They are connected to an edge with cost 10 and also Uh, there is a pass between them with cost n plus 1. So if we run, I mean, the optimal solution will connect this top and bottom pair with a edge with cost 10. But if we run this legacy mode going algorithm, we can see that every horizontal pair will grow a mode and they color this path with cost n plus 1. So we will select this path instead of the edge with cost 10. And you can see that our solution is almost twice the optimal solution, and the local search and extension won't change anything here. You see, the problem is that while in the optimal solution, all of these pairs are separate, we are connecting all of them together, and these horizontal pairs are affecting this top and bottom pair and forcing us to select this with cost n plus 1. I want to call this horizontal pair as a dummy pair. If we add this dummy pair to any edges of our graph, they can like color that edge and force us to select that edge. So that's the problem. That's the problem that we can also call it the over connectivity. And we find out that we can detect these dummy pairs through the term that we call it autarkic pair. The autarkic pair is more general than this dummy pair. So what are autarkic pair? Autarkic pair are a two group of vertices. That vertices in one group are very near to each other, but they are far from the vertices in other group. And these vertices in one group needs to connect to vertices in the other group. They are pair of each other. And the modes that connect these two vertices together almost only contains these vertices. It doesn't contain other vertices. Basically, it's like they are isolated from the other component. So it's like they modes grow and color all the paths between them, connect them, and then other component after that will may use the color that the mode has. So this is the autarky pair. We try to detect autarky pair, and then the algorithm works like this. So we detect autarky pair, and we add a zero. We basically void the a path between one vertex from this group to a vertex from the other group. We void the path between them, and it means that we add it to our solution. And after that, since there is a path between them in our solution, we can assume that there is a zero cost edge between them, and then we rerun the mode scoring algorithm again, the legacy mode scoring algorithm again. So this time, no modes around this. I mean, this time if we run the legacy mode scoring algorithm again, these two groups will connect to each other through this zero cost edge. And I want to show you in an example why this helps. For example, here, after we detect all of this as a autarkic pair, and we buy the shortest path between them and add a zero cost edge between them. If we rerun the legacy mode scoring algorithm here in this instance with this zero cost edge, this time this horizontal pair they won't grow any moats around them because they are already connected through these zero cost edges, and this horizontal pair wouldn't force us to connect this top bottom pair through this long path. So this time this top bottom pair will connect this edge with cost 10, and we will have a similar solution than the optimal solution. So this is the general idea of our work. So basically, we first find the solution through the local search, which is if our component is similar to the optimal solution, which is the case for Shine tree, we would have a good solution. But if we are over connecting, we can use like autarkic pair to find a good solution. Or if we are under connecting, we can use the extension and then run the local search again to get a good solution. And I know that in general, it's a combination of this. I mean, we are over connecting some vertices and other connecting some vertices. But based on which one is the major, we show that one of these solution would be better than to approximate solution. That's it.